let's consider the following example. We are going to integrate the function f of z, which is given by the following expression. Y, which is the imaginary part of z, minus x, the real part of z, minus 3x squared I. So the real part of this function f is just this, and the imaginary part of it is this. And we are going to integrate the function f of z from O to B in two different directions. First, we are going through this curve C1, which is from O to A and from A to B. So we are going along this curve. And secondly, we are going to integrate over this curve, C2, which is just the straight line from O to B. Okay, we know first we need an expression for these curves. We need some set of t, and an expression for this. So let's start. This set of t may be chosen to be 0 from O to A in the x direction, and we can choose it, for example, to be equal to t in the y direction, or the imaginary part of this function set. If we do this and choose the parameter from 0 to 1, we will, when t is equal to 1, we will be in the point O. And when t is equal to 1, we will be in the point I. Recall that the point A here is equal to the point I. The point B is equal to I plus E. I plus 1. Okay, so using this function set of t, we obtain that the derivative of set with respect to t is just equal to I. Now we know that the function f of z has this description, so we need to replace set with this this function set of t, and this function set of t is described by real part x of t and the imaginary part y of t. So let's replace every place where we have x, we write x of t, and every place we have y, we write y of t. This is what we have done here, and we then substitute these expressions. We have x of t is always equal to 0 in this straight line, and y of t is equal to t. So substituting this, we obtain this simple expression, which is just equal to t. Now we recall that the integral over the curve from O to A, it's given by this general expression. We in this case we start with 0, t equal to 0, and end with t equal to 1, because that's our choice. And we have f of set of t. What's that? Well, we have already written what it is. It's equal to t, so it's very easy to find this function. And we have also found that the derivative of set with respect to t is equal to I. So we substitute these values into this general expression and get this integrand. So this is just a constant multiplied with t, so the antiderivative of this function is just half t square I. And we need to use the limits 0 and 1. I've forgotten that here, but using this we obtain that this integral will be I over 2. Okay, then we have finished this integral OA. Let's integrate from A to B as well. In this case, set of t could be chosen equal to 10 t plus 1I. Recall that the imaginary part, or the imaginary part, is constantly equal to 1 along this line. Just recall this. Along this line, the imaginary part is just equal to I. So the imaginary part should be constantly equal to I for all values of t along this. The real part goes from 0 here to 1 here. So we can just use the function t as the real part of this function set of t. So let's do that. So we have x of t, the real part is t, and the imaginary part y is equal to 1. In this case, we obtain that f of set of t is equal to same as above, but in this case we have to substitute x of t equal to t and y of t equal to 1. Doing this, we obtain this expression. We obtain this expression, and finding the derivative of set with respect to t is easy. Also, the derivative of x of t is just 1, and the derivative of y is just 0. So therefore the derivative of set is just 1. So we may substitute this into the general expression in our case. Note that maybe I didn't emphasize this enough. Also in this case we choose a to be 0 and t go from a equal to 0 to b equal to 1. So therefore we have these limit points for the integral, and substituting this we have now an expression for f of set of t, and we have an expression for this derivative of set, and substituting this into this general expression, we obtain this integral, which is very trivial to compute. The antiderivative of it is just this. And using the limits 0 and 1, we find that the integral is half minus I. So now we are able to find the integral from over C1. It's the integral over OA plus the integral of AB. So both these integrals are computed, and we add them together and get the sum of it equal to half minus I over 2. So let's turn to the second integral over C2. That's only the integral over the path from O to B, the straight line from here to the point I plus 1. And it's easy to see that using this function we have a description of this curve. We can also in this case use A and B equal to 0 and 1 respectively, and we can check that this is the curve. This is one expression of the curve along this path. Taking the derivative of this curve, noting that the real part x of t is equal to this guy, and the imaginary part y of t is equal to this t, we obtain that the derivative set of t is equal to 1 plus I. So again we use the general expression for f of z and replace x and y with x of t and y of t, and here we have x of t and here we have y of t, and we substitute this into this expression and get that f of z of t is equal to minus 3it square. So using this expression and the derivative of z of t, we can find the integral from O to B over this function f of z, using the definition of this integral again and substituting these values into this general expression. We obtain this integral, which also is easy to compute. The antiderivative of this guy is just t to the power of 3 with a minus here in front, and inserting these limits, yes, we also should have I from this and I plus 1 here from this constant, and inserting these limits we obtain that it's equal to 1 minus I, which is not the same as the integral over the first part. So we then are sure that these two integrals are not it's not independent of the path, this integral.